Plus it's hot in the school all day. I don't know about y'all, but I've been sweating all day. Okay, so here are some examples y'all gave me for number one. I wanted something with an exponent, and I have things like this, x squared, which is great. 3 to the 4th is great. 9x squared plus 6 is great. 2 squared and b squared. Okay, so here are some things with exponents, which is what I asked you to find. Tell me, just to review some vocabulary. Right here for x squared, if I asked you for the base, what would you tell me? X, and what's the power? 2. What's another name for power? Exponent, right? So we're talking about exponents. Also, sometimes we call those powers. And also notice you can have a base that's a variable or a base that's a number, like this one's 3. Some stuff y'all gave me that had radicals in it. Radical 4x minus 3. Radical b squared. Radical 6. Radical 2. Radical 24. So all of these have radicals in them. So another word for radical is root. Which root are those? What do we call those?
Square roots.
Those are all square roots. But that's not the only kind of root we have. We can take a cube root. We can take a 4th root, a 5th root. How do I know that all of these are square roots? I love what you just said, because they don't have a number written up there, right? Okay, so let me give you an example of something that would be like a cube root. Like this is square root of 24. What's that? The cube root of 24, okay? So if there's no number written, we know it's square root, okay? And that's the only time, if it's not written, it's always implied that it's a 2 right there. So if nothing's written, we understand that it's 2. And the reason why we don't have to write it is it's such a common root that we're like, we're tired of writing the 2. We're just not going to write it. And then for the last one, I asked you to combine these things, and it's the main idea behind our lesson for today. When roots and radicals, or powers and roots, are combined. So here's one. The square root of 24 cubed. That's a really good one. That's something like we're going to talk about today. The square root of 2 squared. The square root of 2x squared. Oh, I already wrote this one, sorry. Okay, so these are some examples where roots are combined with powers. And that is exactly what we're talking about today. Let me see. Some other things I wanted to say. Let's look at, I'm going to sort of break down this one right here for a minute. So we have 24 cubed, and it's the square root. What's the base there? 24. Okay. The base is 24. What's the power there? 3. And what's the root? Right? It's a square root, so we understand that that's a 2. So here's what we're going to talk about today, and I'm going to tell you this again in a minute when I give you your note sheet. We can rewrite this without a radical. We can rewrite it with one exponent that looks like a fraction, where the base is 24, the power is 3, and the root goes there, okay, the 2. And so what we're going to practice today is going between these two forms. We're going to be able to write this thing with a fraction exponent or write it with a radical and a power, all right? And that's the basics of today's lesson. So this is called rewriting rational exponents. what I want you to be able to do by the end of the lesson is explain this to me. Why is 9 to the 1/2 power equal 3? Why is that a true statement? You don't have to be able to answer that now, but think about that as we're going through the lesson. Why is that true? By the way, you see how this is kind of where I'm going. This is my base. The 1 is my power, and 2 is the root. Okay. All right, so let me get you your notes. Keeping this stuff in mind right here, okay, that those are equivalent forms. They're two different ways of writing the same thing. This way is with a fraction exponent. This way is with a radical. Okay, two different ways, and that's what we're going to practice here in a bit. Oh yeah, I forgot I put this in here. I wanted to show you a real-world example of when you might use exponents that are fractions, because we always are using exponents that are just regular powers. Quadratic formula, Pythagorean theorem, or not quadratic formula, Pythagorean theorem for sure. But here's one. It's kind of hard to see, so let me write this out. D equals P to the 2/3. Now, I'm not an astronomer, so I don't really know how this math works. But the reason why this formula exists is because the planets go around the sun in ellipse form, elliptical, right? So the thing is that if they went around the sun in just a circle, because a circle is the same distance all the way around. In fact, if they did go around the sun in a circle, that's the definition of a circle, all the points equidistant from its center. It'd be real easy at any time to measure how far a planet is from the sun, because it would be the same all the time if it was a circle, but it's not. It's the stretched out circle called ellipses. And so that requires a different kind of math. And so some famous person, Johannes Kepler, in whatever year, 500 years ago or however, 1500s, right? So I was close, 500 or so, found that this formula, the maximum distance that a planet is from the sun at any given time is D equals P to the 2/3, where P is the amount of time it takes a planet to go around the sun. And so what are some reasons why that formula would be important? Why would we care how far or close something is to the sun? Weather, yeah. All I can really come up with is weather. I don't know. Astronomers, plus just seasons and predicting, and people who are smarter than me, they would know why they want that information. I don't really know. But anyway, I thought this was a really cool example of using a fraction for an exponent. And plus, I really thought it was cool because look how simple that formula is. But it's like crazy math behind that formula. That some, you know what I mean? That really smart person came up with. Or like Einstein's formula. I mean, that's a really simple formula as well. It's so straightforward, but the math behind it is bonko, right? It's really hard. And so I just think that's fascinating that these people get like just obsessed with it, and they are just so curious, and they spend so much time thinking about it, and they just are passionate, and they just keep trying and keep trying and keep trying, and they come up with this kind of stuff that exists in nature, but it takes a really smart person to do all the math to come up with those formulas, and then it predicts stuff, like actual real-world stuff. I think that's crazy. Humans are amazing. I could never sit down and yes, no more. So we have this formula, and I just really liked about the fraction exponent. All right. So here we go with our notes. I want to begin by just writing down this general form. A to the m over n. This is an example of an expression that has a rational exponent. So do you remember we've been using this word rational a lot the last unit? Do you remember what I told you that means? What does rational mean? It's another classroom appropriate F word. It's not factor. Fraction, that's right. So that word ratio, remember, is our implication that we're working with something in fraction form. So in this example, so where's the fraction here? M over n, all right? So our exponents are fractions. So that's the main part of today's lesson. So when I'm saying that we're going to rewrite rational exponents, I mean our powers look like fractions, and we're going to rewrite them with radicals. We're going to go back and forth between these two forms right here. So a to the m over n, which is the base here? A, right? So A is the base. Do you remember from our warm-up which one is the power? M. The one on top is the power. The root. The root. Like if it's a square root, what would n be? 2. Very good. If it's a cube root, n would be 3, right? And so I always think it's easier to remember which one is the power, because like if there was no n there, then obviously m is a power, right? And when it has a denominator, though, that's going to be your... Oh, sorry. Oh, I guess that doesn't... Yeah. From my angle, I can't see it, but I guess from yours. So it seemed to make sense to me. So a to the m, but like this, that's a power, right? When you add a denominator, that means you're dealing with a root. And so we can take that rational power or rational exponent, we can rewrite it as a radical, but there's two different ways we can do that, right? So I'm going to show you both ways. The first way is to write the power first. Okay, we're kind of separating the power from the root, and I'll show you why we're going to do that later. So if you write the power, separating it from the root, then you would write the root as a radical like this. Okay? The power is with the base. The root is on the outside of the radical. That's one way of doing it. Power first, root second. What do you think is the other way I could do that? The opposite. Root first, power second. And here's how that would look. The root first would be that, the n root of a, and then this whole thing would be raised to the power. Okay, so the reason why we would ever want to separate the power from the root is to make math easier. And we're going to be simplifying and actually doing the math in the last part of the lesson. So we have these three sections on our notes. They are all separate from each other. So we're going to fill in this section vertically, then this section vertically, and then this section vertically, all right? We're going to practice in this first section writing as a radical. So I'm going to give you some stuff with fraction powers first, and you're going to write it as a radical. And then in the next section, we're going to do opposite. And then in the last section, we're going to rewrite, and we're going to actually do the math. So here's the, going back to this first section here, here's our first example I want to do. M to the 1/3. I want you to write down how you think that would look as a radical. So just write M to the 1/3. How do you think that would look as a radical? Okay, so here's what I saw in some of your papers. Some of you are hesitant. Some of you have already nailed it. M is your base. You're rewriting it with a radical. The power is what? And the root is 3. Okay. Do I have to write that 1 there? No. So an equivalent expression would have been just this. Okay, either of those is fine. Try this one. 8 to the 1/2. All right, so I see this on your papers. This is an actually interesting problem because this right here, 8 to the 1 radical 2 is fine. But in this particular problem, that 1 I don't have to write, and that 2 I don't have to write. Right? You can write them, it's fine. A power of 1 is the only power you don't have to write, and a root of 2 is the only root you don't have to write. Okay? And so it's fine to write this one with the 1 and the 2. My concern is that if you were going the other direction and you just saw the 8, you just saw this form, remember that that's a 2 right there. It's implied. Okay, do these two. 5 to the 2/3 and 3x parentheses to the 2/5. Okay, so number 3 is correct. 5, the 2 is in the radical, right?
Yes.
Okay, the 2 is in the radical. I'm just going to be picky on it, just so everyone, like if anyone's looking at this on Google Classroom, they know. So that's 5 squared cubed, okay? And this one here is really, really close. I want to bring your attention to something. The way it's written, just the x has the 2 power. But what's going on here in the original problem? Is it just the x that's to the 2/5? So what needs to be in parentheses? The 3x, right? Because it's all of 3x that's getting the 2 and the 5. That's what I was trying to get you to get to. So, all right. So here, all right, so there we practiced going from exponent powers, exponent powers, fraction powers to radicals. Now we're going to go the opposite way. I'm going to give you radicals, and you're going to write them with fraction exponents. Yes. Rational powers. Okay. So here's the first one. How would you read this out loud, do you think? What root is it? What's the root? The root is what? Yeah, so you'd say the 7th root of x cubed. Okay. So try and write that, rewrite it with a fraction exponent. Hayden, what did you write, please? What did you write?
X.
3/7.
3/7.
To the 3/7. And I pretty much saw that on all your papers. Okay, good. All right, next one. Square root of 9. How would you write that? With a fraction exponent. Yeah. 1/2, right? 9 to the 1/2. Because why? It's the square root, right? So number 3 is leveled up a little bit. The 5th root of 4 times m. How do you think that would go? Okay. I really like number 4 perfect. And I mostly like number 3. Look at what do you think's going on in number 4 that we could add to number 3 and make it better? Parentheses. Because what has the 1/5 exponent right now? Just the m. But we need it to be 4m. Okay? So 4m parentheses to the 1/5. What? Did you answer your question? Your own question? Okay. And then number 4 looks really good. All of 6x to the 7th is in parentheses raised to the 2/3 power. Be sure when you're writing, in this case, that your 2/3 looks like it's up in the air as a power and not next to the parentheses, because what would this look like if someone wrote it like that? Fraction times a fraction, right? It would look like a multiplication instead of a power. All right, so here's what we're going to do now. We've gone from, in the first section, we went from fraction or rational exponents to radicals. This section, we went from radicals to rational exponents. Now we are going to use those skills to actually calculate some math and figure it out. Like, because for example, right here in number 2, we rewrote that, but we didn't actually do the math on it. It's 3, because why? The square root of 9 is 3. All right. So here's an example for simplifying. Let's say we have 125 to the 2/3. Now, up here in the top part of your notes, I gave you 2 different ways of writing that. And I'm going to show you those two ways now, and we're going to talk about which one we like better for the actual math, okay? We can write this with the power first and the root second. We can also rewrite it as the root first and the power second. And I want you to try and do your order of operations on those in your mind, not actually, but just imagine it, and tell me which one you think would be easier to do. That first one you would do, you figured out which one you think? The first one we would do 125 squared and then cube rooted. And on this one, we would do cube root of 125 and then square it. Which one, top or bottom? The bottom. The bottom would make for easier math. Okay? So that's the order, that's how we're going to do it here. So I want you to make a note to yourself on this section that it's easier to do the root first and then do the power second. It's easier to do the root first and the power second. So if we're going to be actually doing math, though, we need to review what it means to take a root. Like right here, this is the cube root of 125. What does that mean I'm looking for? How do I do that math? What's the concept behind that? Kind of. So Noah said, what three numbers make up 125? And that's on the right track. Yeah, because it has to be the same number. What number times itself 3 times would be 125? 5, right? Because let's say you have 3 5s. 5 times 5 is 25, times 5 is 125. If you get stuck and you're like spending some time on your calculator and you're not figuring it out, do a factor tree. At any time you can do a factor tree of a number and it's easier to see. But I won't be giving you really complicated numbers. So the cube root of 125 is 5. So I took the root. Now I need to take the power. What's 25? No problem. 25. Okay. So now that we talked about that, I'm going to give you some to do on your own. That's true. Number 2, that is not true. That's a dork. Try this one right here. Go fast. Okay. I don't hate you today. All right, so here's what I saw in your papers. You rewrote this with the root first and the power second. What did you get for the 5th root of 32? 2, right? Because 5 2s, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. The 5th root of 32 is 2, and then we're raising it to the 2nd power, and 2 squared is 4. Try these real quickly. They'll go faster. Okay, let me write it first before I talk about it. So look at these and tell me why I said they're going to go faster. They're just roots. There's no number on top, so there's no second step. What y'all get for the 4th root of 16? 2. And then 5 on the bottom, because the 1/2 root means a square root. All right. I have a practice worksheet, but we'll get to it tomorrow. Yes.